This is Adam Jaeger from the University of Georgia, and I'll be talking about composite empirical likelihood.
Thanks, Ross. No, thank you very much. I appreciate the opening. Probably as some of you guessed, Ross and I are not overlapping colleagues, but we do attend, he graduated from UGA, and I think he left a year before I started. So this is obviously my dissertation topic. So if I had to sum up basically the whole point of my research from this aspect, this is the best quote I could find. So for those of you who have heard of John Tukey, if you're ever asked a question about who did this in statistics, you can just say Gauss or John Tukey. So, basically, but Tukey had this idea that it's better to get an okay answer, but at least be asking the right question, as opposed to these precise answers that are just really, really wrong. So this is the essence of what we call non-parametric statistics. So I'm going to walk you through some basic stuff. You've probably heard about it. If not, that's fine. So one of our biggest tools in statistics is something called the likelihood function. So you may not realize it, but almost every statistical technique can be designed around this idea of a likelihood. So we have this data. Notice I'm being vague. Z is just some k-variate data. I'm not even saying if they're equally matched. If I have matched pairs, it's just some clump of observations. In statistics, we always kind of start with this one assumption that there is some true probability function that describes the behavior of our random variables. So f is just the probability function. Z are the random variables. Now theta are parameters that define certain specifics about the function. So in this first case, we would ask a question like, give me a value of theta. What's the probability of my data looking like this? Well, that's not what we do in real life with data. We have data and we want to say, okay, what is a likely mechanism or model for where the data came from? So Fisher just came up with this idea of we will just reverse the probability function. Instead of asking, given a theta, how likely is a certain outcome, we have, okay, we have this data, how likely is the parameter space? So you can take that function, maximize it, you get something called the maximum likelihood estimator. Believe it or not, x bar is actually the maximum likelihood estimator for almost every probabilistic function. Another piece he came up with was something called the Fisher information matrix. The main reason I'm writing it out is we get this very interesting relationship that the first derivative of the likelihood squared expected value is actually equal to the second derivative of the negative expected value. So this is based on something called the Bartlett correction. I'll show you why this comes into play later. And as we'll see, the Fisher information matrix actually allows us to describe some of the probabilistic behavior of our estimators. So given very few mild regularity conditions, we can actually show that our maximum likelihood estimator converges to standard normal distribution. It's going to have the same mean as our parameter, and you can actually find the variance using the inverse of the Fisher information. Another interesting fact is Krumau-Rao have this result, it's just called Krumau-Rao lower bound, is that the minimum variance you can get out of any estimator is never going to be less than you see using this method. So what this means is any maximum likelihood estimator is going to have the minimum variance possible. From a statistical standpoint, that's a good idea because it means we don't have to worry about these wild fluctuations. This is the other main result, and this just basically says that coming up with any sort of statistical test, really straightforward using your likelihood. I won't get into the details of why it's -2 in the log, but the whole idea here is you want to test some set of your parameters. That second set, the new sub hat, that's just saying there are additional parameters for the distribution, but you're just not interested in them statistically. So you come up with this test statistic. Well, it winds up that asymptotically, you have this nice chi-squared with your degrees of freedom being equal to the dimension of the parameter space you're interested in. So again, a lot of statistical techniques rely on these two very basic results. Now, given that what I've just said, you might be saying, okay, so why is there anything else to do with this? It's a great tool, they use it all the time. Well, this is data I work with. So here what we have is we have a functional magnetic resonant image scan from one person. This is a whole brain, time point 1, time point 2. Most of the data I work with has about 180 plus of these. So how would you write down a probability distribution function for a system like this? Well, we can describe it generally, but the amount of time and energy it would take to actually write down that function is just too much to handle. So two basic alternatives that's come out of the likelihood literature, and they actually coincidentally came out the same year, is something called composite likelihood and empirical likelihood. Now, for those of you who have worked with likelihood functions, I guarantee you've actually worked with the composite likelihood, you just may not have realized it was called that. So the composite likelihood is we are, I am missing some stuff here. And never mind, I can explain what's going on the bottom. So we're just going to take our data and basically subdivide our data. Sometimes the divisions are done randomly. Other times they're done with a very specific purpose in mind. So with each of the subset of data, we can also set up a likelihood. So the key here is that each of these sub-likelihoods is in itself a proper likelihood function. And then all we do is we just take all these pieces, multiply them back together, and we have what's known as a composite likelihood. So I've just written down a few examples. This first one, taking the product of your marginal distribution times your conditional distribution, this is actually equal to the true likelihood function, but by definition, this is a composite likelihood, simply because you've taken a likelihood, broken it up into two pieces, each piece is unto itself a proper likelihood. The second one is what is generally called the marginal form, because as you can see, we are just assuming that both random variables are independent, multiplying the probability densities together. The third one's a little weird. You might ask why we would do this conditional form. That sort of form comes up a lot in spatial statistics. If you've ever heard of an Ising or an Ising model, that was the basis for that. So just notice here that we can take this bivariate. We basically have several options of likelihood functions. But then other questions we might want to ask ourselves is which ones are more appropriate. And as we'll see, sometimes we lose information using certain forms. Other times the information we're losing is worth the gains we're getting out of it. So here, because the likelihood may not be properly expressed, that actual composite one, we have to differentiate between what's known as the sensitivity matrix and the variability matrix. So if you remember from the Fisher case, both of those quantities would have been equal, the H and the J. In this case, we can't guarantee it. So now our information is in something called the Gadambi information matrix, which is just your sensitivity matrix times the inverse of your variability matrix. A property you can show here is that if you get these are equal for all theta, your composite likelihood is actually equal to the true Fisher form.
And the inverse is guaranteed to exist, right? The inverse in the middle, guaranteed to exist.
Yeah, you have to guarantee that. And actually, if you just look at the form, because you're basically looking at a covariance matrix, and in statistics, this part right here, in statistics, we always assume that's invertible. But yeah, I've yet to ever see a case where you can't invert that. So, but same idea, we maximize this function to get our estimator. Notice once again under regularity, we're getting that normal. This time instead the variance is based on our Gadambi. I believe there is a proof that shows that your Gadambi is always going to be greater than or equal to the Fisher information. Now here's where things get interesting. Same test statistic, but instead of that normal chi-squared, we get what's known as a weighted chi-squared. The simplest way I can explain this is normal chi-squareds, you can think of them as just a sum of a bunch of chi-squares. So the weighted chi-squared is also a sum of weighted chi-squares, but each one has a different number in front of it. So what happens is you are kind of getting this unequal balanced sum. So the weighted chi-squared is different than the chi-squared. And one of the hard things about this is that the closed form for these to even find the probabilities are very confusing. It's something called an incomplete gamma if memory serves. But as I'll show, there are ways to estimate these. So that was composite likelihood. Now empirical likelihood just goes, okay, just forget about even trying to deal with the probability function itself. So this may look a little weird, but what's going on is each of these p sub i's, you can think about it as a weight. Or if you want to look at the likelihood example for any fixed value, for any fixed data point and a parameter value, you get some number. So these p sub i's are basically giving a weight of how each observation, how much influence it's putting on your choice of parameters. The pi greater than 0, that's just standard probability. You can't have probabilities less than 0. The constraint equals to 1 is arbitrary, and it's not. This whole technology is based on what's known as a cumulative empirical distribution function. So by definition, all your weights have to sum to 1. But we also have that here because if we did it, the maximum value would always be infinity. We can't use that. The third part, that's the part with empirical likelihood that you really get to choose and play around with. The z sub I theta, that's what they call an estimating equation. For example, taking your data value minus a parameter, that would be an estimating equation. If you've heard of Huber's M estimators, same class, but pretty much any sort of standard or non-standard statistical measure we use can be written as a M estimators. The only requirement is you're assuming that the expected value of the way that equation's set up is going to equal 0. So the bottom line is just a quick example. If we were interested in performing inference on the mean parameter, there's our empirical likelihood. So notice here, I haven't specified a probability distribution. Basically, all I need is some data. Oh, here's the relevant part I see you looking, is that I'm just doing my data point minus the mean, multiplying by the weights, adding them up. They're going to go to 0. Interesting fact that when you maximize this, you actually get x bar. So once again, for the estimator, we just maximize this function again. Notice once again, given some regularity, we get this normal. These normals keep coming up with these sorts of estimators. Now we have this is our defining our variance covariance matrix. This is something I've kind of been trying to figure out just psychologically how to explain how this relates to Fisher likelihood and composite likelihood, and I'm not really sure yet. But if you look, we're basically taking into account the variation of your data, and then we're just kind of looking at derivatives of what you're interested in. The last bit is we can actually show that same test. This time we get that chi-squared with p degrees of freedom again. So the chi-squared isn't that surprising, again, given the fact that in probability, all those weights, if we collected enough data, so should be so close to the true probability function that what we're estimating is pretty much what the truth is. So again, at this point, you might be going, we have these other two great methods, so what am I contributing? Well, the composite likelihood has one catch. Each of your pieces also has to be correct. So that's to say that for any subset of your data, however you're setting it up, each piece also has to be exactly defined correctly. So if any of your assumptions about the distribution are off in your composite likelihood, it falls apart. I think now empirical likelihood really hasn't caught on in statistics, and I think that's mainly because you run into a lot of optimization problems. Again, when this technology was developed in 1988, a lot of the simulations, they almost had to approximate things by hand. As far as finding out Lagrange solutions to the problem, they didn't have very good optimization programs back then. So empirical likelihood really is just not viable when you have a huge data set like brains. So my question was, what if we take both these features and try and extract the best elements of both? So that leads us into this idea of composite empirical likelihood. So what we have here is I'm going to describe a non-parametric approach using the piecewise construction of a composite, but I'm going to use non-parametric pieces for my likelihood objects. A couple of interesting things come up. The theory we're seeing actually mirrors a lot of what you see in likelihood theory. In fact, there have been a few results that we were actually expecting simply because they made sense based on all the other research. From an application standpoint, the separation of the likelihoods, this allows you to take advantage of parallel computing. So I also have something near the end to show you that you get huge gains using this if it's just a time constraint. So I'm just going to focus on kind of this two-piece composite empirical likelihood. So I will say that we found that once we got the theory worked out for the two pieces, extending to a general J case is actually real easy. But I think with the two, it's just a lot easier to see what's going on step by step. So notice that this piece up here is defined exactly as that empirical likelihood I showed you. This piece down here is defined exactly as that empirical likelihood. So it fits the definition of a composite likelihood. That is the product of proper likelihoods, each of these being a proper likelihood. So just a few basics. So once again, by definition, we are going to define our maximum composite empirical likelihood estimator as just the theta that gives you the maximum value possible of this object. We have also seen that given a few regularity conditions, mainly guaranteeing certain things are invertible in that certain derivatives exist. Again, nothing strenuous. We once again get a normal, and this is where things really start to get interesting, is if you remember from the regular empirical likelihood, our W was just kind of this top piece. So here, we're basically getting the sum of these two. From a statistical theory point, this is actually kind of expected, and again, I haven't shown the details, but going through the proof of this, it winds up that you're actually adding up two items that converge to a standard normal. There's a very straightforward theorem that says when you add up two normals, the variance is just the sum of those variances. The second part, which kind of got cut off, is again a little weirder, but if you look at this chunk right here, this is accounting for the correlation between those x and y variables. So this is actually describing the correlation. This is the variance of your x terms, variance of your y terms. So it's pretty close to this idea of looking at correlation and then some function of the derivatives of your estimating equations. So again, this is another one where I haven't quite been able to make sense of it in context of the other empirical likelihood, but it did give me some ideas.
Your definition is symmetric about the two parts, isn't it?
Yeah.
So in other words, if you interchange the rho and v and w, you will see the distribution will go to v inverse w plus v inverse. Of course, the definition depending on how you put those in there. So even that quadratic form.
Actually, that's what we were talking about this morning.
Yeah, it's curious. I mean, how you define the quadratic form, and therefore you get an expression apparently asymmetric, but because definition dictated, so there, if maybe for matrix theory, there's some reason to see why that's the thing.
Let's see if I can get this on full screen. That's much better. Okay. Thank you. I planned that so you could. So, but you're right. I mean, this was one like this part. When I saw this, I'm like, okay, that's making a lot of sense to me. And again, I tried to put this in context because again, another statistical another thing with statistics, when you take two variables, add them up, your variance is going to be the variance of one plus the variance of other plus or minus 2 times the covariance of that. So this is kind of filling that same role, but you're right, it is a very kind of weird, unexpected form. The good news is I can say I have run enough simulations to know that this is not wrong, but what I am struggling with is just kind of what does that mean? The reason I wrote it like this here is because I wanted to do that in parallel between the Gadambi information matrix. Because another thing you'll notice, if the covariance goes to 0, the v drops out, those cancel, you're back to that first case. So, but yeah, that is long-term future research question of partially what is that saying and how can we handle that. So, second thing was the test distribution. So, I remember about 6 months before we finally had the proof for this, I was talking to my advisor and she said, trust me, you're going to get a weighted chi-squared. Well, she was right. So you get this weighted chi-squared. Again, I won't go into how you actually find the weights. That's what the lambda's defining. I will say loosely that the weights are based on, you have to know the variance and the covariance of your two random variables with those estimating equation transforms, and you have to be able to write down the expected value of the derivatives of the equation. Long story short, it's pretty complicated. Now, you can actually estimate this using the data, and I'll show an example where we do that. But at this point, my thought was, this is a good solid result. It matches up with the composite likelihood, but just from an applicability, a lot of people get hesitant about using a weighted chi-squared, and again, it's a thing that you need a lot more information to work with it. Whenever you use your data to estimate things, you run into the problems of your estimating of estimates, and things don't always work out as well as you like. So, just kind of at this point, we're seeing an asymptotic distribution that isn't too surprising. Again, like I pointed out, the reason I wrote the variance-covariance matrix in that form is because I've been trying to think about, okay, can I think of W as a sensitivity matrix and then W plus V as a variability matrix? I don't know, but long-term I'd like to be able to come up with something that says this is really the non-parametric equivalent of what we see in likelihood. like I said, if you go back and look at these results for just a regular empirical likelihood, they are, for lack of a better word, almost predictable. The asymptotic behavior, again, predictable. We get that weighted chi-squared, and that weighted chi-squared is giving us another hint that there may be information we're ignoring. Because remember, we're splitting up these two likelihoods, so any correlation between x and y is just not accounted for in the likelihood function. So that got me thinking about, okay, how can I make sure that all the information is accounted for so I can go back to that weighted chi-squared? So I started looking just at a few general cases. So this was my first idea. So let's just say you have a bunch of data. I'm just going to assume it's univariate normal, IID, and I'm just going to take this sample and randomly split it into two pieces, x and y. So if I just use that single z, for the normal likelihood function, my estimator converges to a standard normal 0 sigma squared. If I use it for the empirical, I get the standard normal 0 sigma squared. Composite, looking at x and y, we get the same thing. And our composite empirical, we also see the exact same distribution. Another thing you can show is that under this condition, you're getting the test statistic is asymptotically chi-squared 1. So what hit me was that the reason this was happening is because I had made the assumption that x and y were independent. So that got me looking back at the previous equation, and I was able to come up with a special case for the test distribution. Now, one of these conditions is pretty obvious, that we have to assume our covariance is 0. So what that allows us, what happens is that since we're getting the asymptotics, and because, as I mentioned, the main pieces involved in this, in the test statistic, converge to normal distributions, covariance of 0 actually guarantees us independence. The second one, this surprised me that I had to enforce this, that this only works if you have no nuisance parameters. I have not figured out exactly what's going on with that yet. But if you don't have any nuisance parameters and your covariance is 0, you get this nice little result that you get that nice chi-squared with p degrees of freedom. So at least on one step, it's going back to everything we've seen in composite cases, empirical cases, so on, that all the information concerning the relationship between these two random variables is accounted for. So we get that standard chi-squared. So this got me thinking even further. So like I said, if you notice, our covariance is not just about the data itself, but it's about the estimating equations, which means that certain estimating equations may allow us to essentially transform the data in such a way that what was correlated data is no longer correlated. And I'll actually show you a few examples where that works. So this is where we started thinking about these ideas of using conditioning equations, because there is a pretty basic statistical theory that says any bivariate probability you can write it down as a product of marginal and conditional. By definition, the marginal and conditional are surprisingly independent. So other things I've discovered is, as I mentioned, you have to worry about the nuisance parameters. Well, if you're working with nuisance parameters, I have found one case where you can also get that chi-squared of 0. But again, the thing is, with the nuisance, you do need that 0 correlation. So it's a necessary condition, but unfortunately it is not sufficient. So the idea on using this conditional just came up with, let's just look at a basic linear relationship. So I've kind of restricted this to cases where you're looking at just ordinary least squares modeling. You can extend this to generalized linear modeling, but I haven't explored those cases because you run into some more problems. But this is just based on kind of the simple idea is that when you have correlated data, in a fair amount of cases, you can usually express the mean of one of those random variables in terms of like a marginal mean plus some adjustment based on what the other parameters, what the other random variable's doing. So if you look in the literature, yes.
Is there a mistake in that equation? So you have you cannot transpose x before beta. So is that what you have two transposes, but only one, I guess, should be.
Let's see, x transpose. Yeah, I shouldn't have transposed that second one.
Okay.
Nobody caught that at my last talk, so thank you. This is what happens when you come to a math department. Let's see. How did I do? Yeah, that should be y minus x beta, so thank you. I feel like I should write that down, but So okay, so pretending I did that right. So for apparently you guys are better at this than I am. But that's just a basic ordinary least squares equation. So if we make general assumptions, constant variance in the random variables, so on, so on, so on, we can just use that OLS equation. So the reason we can't just do the y minus x beta is I actually have two parameters, so I actually need two equations. So this is our first idea. This was just the idea of using this conditional marginal form. So I'm just going to assume one of my random variables has some mean. I'm just going to call it mu sub x. The other one, I'm going to condition it on x, and I'm going to assume that we have that standard linear relationship. So this is my parameter of interest is mu sub y, and this part is kind of is basically I'm trying to correct for the correlation. If these two variables were uncorrelated, this would be 0, no problem. So if you work this out, you have these two sets of estimating equations. So this is just the estimating equation for the normal that I showed you before. This is where stuff starts to get fun, is that for each observation we're subtracting the mean, this linear component. This m sub mu x is the fact that the mu sub x is being estimated based on this set of equations. The second one, and this is where we ran into a few more interesting problems, is that second part of the x transpose times y minus x beta. So this is your set of estimating equations. So you can see we have 1 in the g sub x, 2 in the g sub y. So in order to get a weighted chi-squared, we need to figure out the conditions on which the correlation between that is 0, and that is 0. Well, it winds up there is one strange condition we have to meet. So if we can show that the expected value of the square of x times y is equal to the covariance of x and y times the third moment of x, we're okay. That's kind of a huge thing to check, but what I did find out through a little reading is this does hold for a normal random variable. Now, I don't know if it's going to hold for anything else. This is another thing I'm working with, trying to figure out if there's a way I can simplify it or at least give it more of a kind of basic idea, so when you're working with some data you can go, okay, we're probably meeting this condition. Because this unto itself can be a little nasty, and also this requires knowing the probability distribution, so if you know this, why are we doing this in the first place? So, assuming we meet these conditions, this whole mess, we get that chi-squared with 2 degrees of freedom. So, I will show some simulations using that result, and actually it winds up that using this form gives us virtually identical results to empirical likelihood. So here was a conditional set. Now the reason I wanted to do these is because one of my interests is in large space-time systems like the brains, climatological statistics, so on. So this is, even though I'm just doing it for 2 pieces, the ultimate goal is that you're looking at any location, conditioning on everything else going on around it. So this is just extending what we saw, except this time I'm conditioning on both sets of equations. Again, like I said, there are times to do this. There are times not to do this. So again, set this up. Now, one funny thing we find with this is the only time that you even have a chance of being guaranteed independence is when rho cubed is equal to rho, which means that the data either have to be perfectly positively correlated, perfectly negative correlated, or not correlated at all. So when I saw that at this point, I gave up checking the other 3 conditions, because I just kind of went, okay, this is one of those cases where we are just going to have to estimate everything for that weighted chi-squared. So now on to the simulations. So standard fare, first of all, we check ours. This second equation right here, this looks a little weird, but this is that empirical likelihood I showed you at the beginning. So I'm just taking my x and y observations and just slapping them together as if it were a single vector of observations. So this would just be assuming that we drew data and we didn't know if there was any relationship, we didn't call anything x and y. This second one, this is the form that was used for creating confidence regions. The only thing I've changed is instead of having 2 values for the mean, I just go down to 1. So this one is, in theory, accounting for any correlation between the data. This one is completely ignoring it. what I'm going to show you is this one is pretty good, that it kind of adapts to whatever it's being given. So use the kind of standard fare random distributions, bivariate normal, bivariate chi-squared, bivariate uniform. Main reason for this three choices was a couple of reasons. You seem to always use the normal. On the earlier papers for empirical likelihood, they used chi-squares a lot just because it was a very skewed distribution, so they could look at convergence rates. I also did the uniform because I wanted something kind of fairly straightforward and predictable. So we parameterized all these so that all of them have means of 1, variances of 2, so that way we're not comparing. We're only kind of looking at how the shape changes things, not how the parameters do. We messed around with some sample sizes and correlation values. I'm not going to show all of them, but I'll show some of them, and I think it'll be enough to see what's going on. The last thing here to notice is that in this setup, I could have actually computed the exact eigenvalues for that weighted chi-squared because I know where the data are coming from. But because we wanted to see how this would perform in, quote, like a real-life situation, I would do what we would have to do in real life, is that I am going to use the data to also estimate the eigenvalues for the weighted chi-square. So keep in mind there's also some level of error in the chi-square distribution itself. But it winds up that is actually not the end of the world. So when we have uncorrelated data, so first thing notice, all our means are lining up. We should be getting about 1. I didn't show here, so you can trust me, I'll talk about, if you want, I'll show you the paper. But our observed variances are coming very close to what the theory says. The average length, I hadn't actually worked out any theory for that. I was just kind of more curious to see how it behaves in simulation. I'll get back to that in a second. This one basically shows how many times that the lower end was greater than 1, which means the confidence interval completely missed it on the right side. This was how many times the upper bound was less than 1, so the confidence interval was completely on the left side. This is just a standard hypothesis test. Your null hypothesis is the mean is 1, gives you a p-value. So here's what really startled me is that with this one, if you remember, that was the one that I said is always assuming there's correlation. You notice here as our sample size goes up, the length is getting larger. I have no idea what's going on with that. But this was not my method, so I wasn't worried. But I mean, this is one where this is really weird. It's almost like saying because it's correlated, it's trying to overextend things to make sure it covers. But you notice here when the correlation goes up, it starts behaving like it should. Other things to notice is that our method is always really close to the one that's completely ignoring correlations. So we're not getting these excessively wide intervals. Here's where we start doing well, is you'll notice when there's no correlation, this method with a sample size of 25 does better. Makes perfect sense. This method is designed when there's no correlation. Because we're estimating things, we're doing a little worse. Once we get up to a sample size of 100, though, we're doing just as well. In fact, we're doing slightly better. And this is even with estimating the eigenvalues and all this. Now, when our correlation increases, notice we're doing better than the one that ignores correlation. Again, you would expect that. But also notice that we are keeping up with the method that is always assuming correlation. I also have results when correlation is 0.1 and 0.9. You see similar patterns like that. So this is for the normal. With the chi-squared, you expect it to take a little longer to converge. Again, skewed distribution, but again, a few quick things. We're still getting the 1s. Our variance is, once again, checked it against the theory, what it should be. This is another case where the LE sub 2, for some reason, the length of the intervals is getting wider. Again, don't know why. But again, notice our method is always coming really close. In fact, in some cases, it's doing better. Once again, we're kind of keeping up with the other methods. And last but not least, our hypothesis tests are doing pretty well. We should be getting about 25. So once we get to a sample size of 100, our method is basically outperforming the method designed for that situation. So again, we're seeing with this composite empirical approach that it really doesn't matter if there's correlation in the data or not. If your sample size is large enough, we'll pick it up. So last bit was a uniform. Suddenly now this one's behaving. So I've kind of given up on that LE sub 2. I'm ready to contact the author and ask him. But let's see, same thing. Numbers are good, variances are good. Once again, our average lengths are about running up with the other ones. And again, we're getting some nice convergence. So the point of these three simulations were just to point out that number one, at least with the univariate mean, we're matching the theory. And here's the big thing, is that when you ask about, is this a good alternative method? Well, yes, and I could justify it even more if you wanted to break this into like 10, 20 pieces and throw it into a parallel computing environment. I have not done that yet because I only have 4 processors. But, like I said, we've worked out the theory for J cases, so not only could we keep up with some of the other methods, we could actually compute these things a lot faster. So then the next thing was 2 mean parameters. So this was what I was talking about for the conditional marginal and those conditional to conditional equations. And this came from the idea that with this method, we might also want to make confidence regions. So again, our setup. So this is the same method I just talked about, except the estimating equations are set up exactly as they were in the 1990 paper I got them from. So this is kind of what we would call the golden case for non-parametrics. So what we wanted to do is we wanted to see how our methods compared to this one. This is that conditional marginal form I showed you where you're just looking at the mean of 1. This one is that weird conditional. So some quick setup. I just mainly stuck to normal for now, and again, that was because A, of that relationship assumption and that weird expected value condition I needed to use the normal chi-squared. I only stuck with the sample size of 25, and that is because these take a while to run. So far, I've only got the results for correlation as a half. As we speak, I'm running a lot more, but at least these will show you kind of the basic idea. And I just messed around with the values of the variance. And the reason for that was I just wanted to prove that it doesn't matter what you call your marginal piece and what you call your conditional piece. So here's the first set. So remember, this is the standard to beat. So I put in the 0, 0, so that's the true value. So what the colors are showing is how many times each method kind of overlaps. So the bright red here is saying that somewhere around 95 out of those 100 confidence regions actually captured that area. This is our method using that composite marginal. So if you look really close, this is actually almost dead identical to this. So this is using the original method, this is using our method, and we're not seeing any noticeable difference. The conditionals get really weird. And I have a couple of explanations for this. Number one, the data generating mechanism do not come from that sort of system. It's not generated from one variable condition on the other variable condition on the first. I am working on simulations for more of that case, so that might be one thing. Another thing I discovered is I'm running the optimization problems with that one, is for some reason, I don't have any problems with the optimization here, but when I look back at some of my error logs, I get weird crashes. It'll suddenly give very strange results, which I think are throwing things off. And I'm not sure why that's happening yet, but I do want to find out. And here I just reversed the variances. So again, same sort of thing. We're getting the coverage we would expect, and that one's behaving really weird. So last little bit. So this time it's just equal variation. So again, this is what we want to see. That's what we're seeing. No idea. So.
What if you make them 10 instead of 4?
I have not looked at those cases yet. Now again, it comes back to the, in theory, I should be seeing the same stuff. I mainly stuck with fairly small variances, just because I didn't want to have the charts big. But I am currently running some more stuff. I am working with more variances. So I would say look for my paper in a few months once I can find a home for it. So I'm actually trying to get some of these results published, but this is what I'm going to try and get published next. But again, I still got a few details to tweak out, because also the theory says that I should be finding that optimal value of beta once I've determined the boundary point. But from a computational standpoint, just throwing in the MLE makes very little difference. And that's something I just want to double check to make sure if that's not like I had the theory wrong, or if it's just that sometimes it doesn't matter in the long run. But yeah, I mean, there is a lot more to be said about I could have done 10, I could have done 0.1. I call this the lazy statistician, that 1 in 100 are the same number when it comes to variation. I think in statistics we call this without loss of generality. That actually is a term.
So the mean is 1 and the variance is 4 or 10 or 1, so that's exactly the setup. So you try to approximate the mean of 1 and the variance is 4 or 5.
Hold on a sec. So well, in this case, this is where the data are generated
Right,
from. The confidence regions are trying to cover that mean, which should be 0, 0.
Yeah, I couldn't read the scale.
Oh, it's okay. Yeah, this goes from -3 to 3.
Oh,
So
okay.
okay, so I'm sorry. Yeah, so the deal with the confidence region is like this little black thing here. That's
Right.
that's the theoretical 95% confidence interval for normal data
Okay.
from this distribution.
Okay.
And so I'm not. So the thing is here, I'm not exactly sure if only 5% of them are falling out. But and also no, I did not do a parametric version simply because comparing this method, which is the original one, with the parametric distributions have been done.
Okay.
So kind of going from that, all I need to be doing is keeping up with this guy.
But what's the size of the feature space? Do you have a feature space? No?
I've not. A, I've not looked at that, and B, I am a statistician, not a mathematician. So, talk to me afterwards because I think you're onto something very interesting, but I'm just not quite sure how to answer that at the moment. So, okay, so at this point, why am I happy? So, again, we're seeing the similar asymptotics. And this is my big kind of hope I can contribute to the philosophical viewpoint of statistics, is that hopefully what we've come up with is a very generalized view on likelihood. Because as I've shown, there are a lot of cases where you can look at this composite empirical, add a couple of specific cases, and all of a sudden you're looking at established likelihoods. I was talking to somebody this morning about math, how it seems with mathematics. You start with these very general theorems, then you find these nice specific cases at work. We kind of go the opposite in statistics. We start with these very specific cases, we build up. So I'm hoping this will be my legacy or whatever. So the piecewise approach, I'm about to show something about that, but even though mostly concentrated on theory, just from an applicability, why is another reason you would want to use this method? Well, this is just a quick chart of CPU time. So this first one, this is the method I'm proposing. This is the same idea, that univariate, this is the bivariate. So this data was the exact setup I showed you at the very beginning. It was just normal random data, mean of 1, variance of 2. So all I did is while I was computing that, I just computed the CPU time, it computed the maximize the function, saved it. So you can see that as our sample size goes up, these are quickly taking longer and longer. I am actually surprised how well R's doing to the point where I've checked the code 3 times. And because again, I really thought this would have started creeping up more just because again, you are optimizing larger and larger pieces. But for whatever reason, keeping them separated does it a lot better. And like I said, I'm especially going to go to 4, 8, 16. And so, but you can imagine just with this, with 2 pieces, imagine if what you were doing with a couple hundred. You could possibly turn a several day optimization into a few minutes.
Is the y-axis seconds, minutes, hours?
It's actually called CPU time, so it's how many cycles the CPU has to go through to compute. So unfortunately, it doesn't have a time component. Now, I can give you a few numbers because I've run these so many times, I've gotten sick off of them. Usually when you have about 20 observations, it only takes like a second or 2 to optimize. Once you're up to 100, sometimes they can take as long as a minute, depending on the data. There's always that random element. And then when you start adding 2, 3, 4 parameters, like just to give you some numbers, the confidence regions, I started rerunning them last Wednesday before I left on a trip, and they're still running today. So like I said, some of these, and the stuff I'm running is in parallel, and it's taking that long. So again, like I said, one of the reasons that empirical likelihood I don't think ever really caught on was that just computationally it can be such a monster. So what am I going to do with this? Well, like I said, we have solved that basically j equals to 2 versus j equals to n. Very predictable results. You just keep summing all these pieces. You're still getting the standard normal. You're still getting the same results out of the test statistic. You don't have any nuisance parameters and they're independent. You get that normal chi-squared. Everything else you have to start working out specific cases. A nice thing about this is you notice that I've been pretty vague on how you divide data. So one of the other ideas Nicole, my advisor, had for this, that if you have like this just tremendously huge data set, like a couple of billion, What about just random sampling, building these random likelihoods, putting them together so you're kind of coming up with an approximation of the likelihood? Or is there one more approximation? But that was an idea that you want to talk about saving computation time, maybe just just randomly sampling. We've also talked about doing that in a bootstrap scenario, which adds kind of a new level of theory to it because you're doing these repeated draws. Big thing I realized is because of these estimating equations, it gives you a lot of flexibility with this method, and that's another appeal of the likelihood, is that basically once you understand how to build a likelihood function, you can do almost anything with it. So what about my brain? Not my brain, but the one I showed you. So this is, just to give you an idea of how this question can be real challenging, this is the simplest model I can think of. So this is based on a combination of what's known as an autoregressive 1 model. All I'm doing is I'm saying, given what happened at this time point, the only information I need is what just happened. And this is also based on this idea of spatial smoothing. So this function right here is simply a weight function where the weight is defined on how close any given point is to the point of current interest. The C sub theta, if you know spatial statistics, can be a parallelogram. Maybe you've heard the term nearest neighbors. Anything like that. It could just be, if this is within an inch, it's 1, everything else is 0. So this gives a lot of flexibility. So this is just, again, simplest model. So this would just be if I had an individual sitting in the fMRI machine for 6 minutes doing nothing. I pulled them out. What this model would tell me is how strong the correlation between their previous scan and their current scan is, and it would give me an idea about how far apart in distance the brain's communicating. So notice that as far as the complexity of a brain, there's a lot of stuff I haven't even accounted for yet. So what we would have is for any given voxel, so the brain data is scanned on what's called the voxel. They scan your whole brain, and your brain's basically laid out on this grid. Each grid point's about 4 millimeters. So each voxel would have an equation set up like this in a matching empirical likelihood. So hopefully I got the transpose right this time. So this would just be the setup, our parameter space. Other things I didn't point out, I could even have a unique phi parameter for each voxel. I could make it constant for the whole brain. Same here, but this is just, I wanted to keep it as simple as possible. So then for any given location, it's just the idea of I'm taking that value and subtracting that formula I showed you. And then put everything together. Finally, I have my likelihood. Well, even in this simple model, I'm talking about over 22,000 pieces of likelihood. And I think each likelihood piece has something like 250 data points in it. So what have I found out? Again, look for the next paper. Or my dissertation if it goes well. So I'll let you know. So other future research questions, I think I kind of pointed out, I've gotten very interested in what is this connection between that W matrix and that H matrix. Same thing between a W plus V and J, because again, I really want to explain this in a context of here's the most general way you can write a likelihood, and then they're kind of coming down to these specific cases. How is this general case relating? Another thing we haven't looked at is this idea of doing a second order Taylor expansion to see if we can get something called the Bartlett correction. This just means we can set things up so it converges a lot faster. So far, empirical likelihood, with one exception, it's been shown that Bartlett corrections work. Another thing that somebody mentioned to me is this idea of a small sample correction. Some of the results from empirical likelihood, instead of using that chi-squared, they actually use an F distribution because you can show that in certain steps of the proof that you're actually looking more like that with a small sample, you're actually closer to an F. So it might just be changing the test statistics. Sometimes you can do little adjustments on things. And like I said, the big never-ending question is what are the sufficient conditions for, yes?
Yeah, item 2 is actually more challenging. When you talk about J2, you have a W plus V. As we mentioned earlier, that you have the distribution, you use W inverse times the W plus V times W inverse. So I just asked J to 3, so you have 3 guys, right?
Yep.
So W1, W2, W3. So how are you even going to define the...
Yeah, tell me about it.
And also, they should be symmetric, right? So if you have the right, there's some example that you can flip the 3 thing, and then in any way you try to describe the 3
right.
set of data.
Oh, you're way ahead of me. I think during one of my 3-hour layovers, I sat down and tried to see if I could work anything out, and all I just had was like 4 pages of try again. So I mean, you're right. These are not questions where I'm like, yeah, I'll have it figured out by the end of the summer.
So you can do J equal to 3 or more, right?
Yeah.
Using all those. But that particular formula, that proof of the distribution, is it also done? So I'm curious about that thing. How many W1, W2, W3?
Actually, you know what? Remind me. I'll send you those results.
Okay.
So, because I'm still typing them up, but again, once you see the results for 2 and kind of see the steps, the progression is pretty natural. But you're right. I mean, it does add a lot of stuff to invert, and you're trying to invert inverses, and you have all these derivatives. I mean, I agree with you. I could probably spend the next 20 years trying to figure that one out. I hope not, but and again, that's kind of more of what I call the question of philosophical interest. You know. So, but it would just be interesting to see if I could go, okay, this is kind of the grand scheme of likelihoods. So, things I think this would be good for, I've already mentioned climatology, neuroscience. I figure if it works on a brain, I can make it work on a galaxy. Social networking. And so again, notice that all of these are kind of these large data problems that as statisticians, we're always tempted to say, okay, well, let's just assume the data are normal and move on. Well, if you've seen data for stuff like this, it's just not, and you're kind of kidding yourself. So based on talking about papers, I'm still trying to find a home for the first one, so just to take a moment. And I forget where I found this, but it made me feel better. So, and that's all I have. Thank you. Questions? Yes?
So I have 2 questions about the, first of all, thank you for your talk.
Oh, well, thank you for coming.
So for the first question, they both have to do with the replications you ran. Firstly, why did you choose 500 replicas?
Oh, This seems like I should have a better answer, but it was more than 100 and less than 1,000.
Okay.
I think also the other reason I chose that is because for those simulations, I found 500 only took a few hours to run. So it was kind of that combination of I wanted to get as many as I could without having to wait 2 weeks. Most statistics papers, 100 to 500 is about the norm. So I'm kind of, so that a lot of, like, again, a lot of those distributions go back to this is what we generally look at. So.
Okay. And the second one just has to do with when you ran your replications, do you know if the seed was the same for like each?
Oh yeah.
Okay.
Yeah, I'm one of my other things is computer programming. So yes, that's advice to everybody. Always set your seed. So like for example, when you saw like using my method or those other 2 methods, it was all identical data on each iteration. So there wasn't anything weird like my results were better because that set just happened to have cleaner data. In fact, purposely I try to make these as unflattering towards my method as I can. Because I figure if I can beat it, awesome.
Thanks.
I'm cool if there are no more questions.